Yeah. Thanks a lot for the kind invitation and for having us. I'll give a very brief introduction before I hand over to the two people that did the bulk of the work and can also answer your more detailed questions. So we titled the talk Interactive and Reinforcement Learning of Language Conditioned Robot Policies. Before we dive into that, I just want to give a very brief motivation to start with. Okay, now I need to get to the right button. Traditionally, robots are programmed in that way. You have some very robot-specific programming language and an expert you need to fly in that does the programming. It's gotten a little bit better with ROS, where you have at least one common language rather than different languages for each manufacturer. But still, what really works well is industrial settings where it's the same thing 24/7 and you don't have any interactions with people and essentially no variations. However, I guess all of our dreams is to make robots go out into the wild. There's obviously more examples. I picked a few that are related to the things we're going to be talking about later in this talk. So think about a butler, servant, household assistant that can do more or less all the things you would want or not want to do in your house and have somebody else do, elderly care, but then also very customized small production lines that are more and more coming up. So that brings a lot of challenges. On the one hand, you have variations in the objects the robot is supposed to interact with, in the tasks it's supposed to be doing, and in the environments. So the dream to some extent is that we are able to get robots that are generalists. And that's where the foundation models and large language models come, so that they're able to handle a wide variety of tasks out of the box, at least to a level that is, so to say, good enough. That's obviously impossible to do by programming everything by hand. So the idea would be to get some learning here. Quite often, actually, the learning methods are inspired by how humans teach and learn. So on the one hand, you have demonstrations by a teacher, and then the student tries to mimic that with a robot in our case, just imitation learning. That works well for fairly simple tasks, and if it's getting more complex, more dynamic, and you really care about the details of the interactions of the robot with its environment, they need to practice. So do reinforcement learning. So those have been extremely well established. Also, the combination of the two of them, and nowadays you also see lots of offline reinforcement learning very effectively get imitation learning data, but then combine it with an optimization criterion or reward function to get more detailed movements. There's a few more things you could consider, and that's something we are going to be talking about today. So different ways of getting prior knowledge in and speeding up the learning. We, as humans, don't learn tasks in isolation. We spent the first couple of months, quite a long time, to actually learn something that's seemingly very simple, just to do. Goal-oriented grasping takes a couple of months. But then once you've mastered that, you actually have some experience and basic knowledge that you can reuse, you can transfer, you can adapt. So somehow you have a lot of basic skills you have either built in through reflexes or that you have acquired in your childhood. So that's one way where you can really think about having these generalists through, for instance, foundation models come in to be able to do more things. And the other thing you see quite often when humans are learning is that they don't learn on their own. They learn in interaction with teachers. So you're going to get feedback from your parents, get hints, get instructions on what to practice more in a sports setting and so forth. So now what we're going to do in this talk is show you a combination of those four things. As I was saying before, the talk is going to be in two parts. Both of them are going to focus on tabletop manipulation. You'll see a little example on the right. So it's about having stuff on a table and then moving it around, putting things into containers, placing them, organizing them, and so forth. That's a very common setting, both for manufacturing and in households. As I was just saying, we're very much interested in integrating prior knowledge to speed up things. And in both cases, we're going to use language as an interface and foundation models to some extent. First part is going to be about imitation learning, where we actually look at the uncertainty, what the robot knows and what it doesn't know, and then also use interactions with the teacher to provide additional examples where needed. And in the second part, we're going to switch to reinforcement learning, where one of the big questions is how the robot should explore, how it should try out new things in order to figure out what works and what doesn't. But that can be extremely inefficient if it's just randomly trying out things. So here we're going to use prior knowledge to guide the exploration. And then obviously you can also think about future work on combining things, using human input to guide the exploration, using uncertainties in reinforcement learning, and so forth. So now let me hand over to Jelle, who's going to present the first part. Come on.
Yeah. So, yeah, thank you, Jens. And yeah, my name is Jelle, and I'm a PhD student and supervised by Jens Kober, and I'll talk about this interactive imitation learning method for pick and place tasks. And it's called Partner, and I will show this as an example of how such interactive imitation learning could work in this in a simple tabletop scenario. So just to connect to what Jens was talking about, this dream we have of robots in the future being able to be general and being able to execute commands that are unstructured, so not in a specific language format, but like yeah, just like humans talk. Robots should be able to understand that and communicate with humans, and being able to work in these unstructured environments rather than in the industrial setting. So in the industrial setting, the environment is usually structured and it's just a repetitive task. But ideally, we would like robots also to be able to be valuable in these unstructured household scenarios. For example, being able to fetch something or to cook or to do the dishes. And as Jens said already, this is very hard to pre-program. So therefore, yeah, ideally, we also would like these robots to be able to learn and also to maybe specialize in certain things or learn new skill sets. And yeah, if we want to learn this from scratch, this might become very time consuming, and it might also be unsafe because this robot has a physical presence. And yeah, when it starts to do random things, when its learning hasn't converged yet, that can be unsafe. So I think one way to do this is by leveraging the prior knowledge that humans have and leveraging the prior knowledge of these foundation models. Because often, yeah, humans know how to solve these tasks or can even demonstrate these tasks or give feedback. And this can be very valuable information to speed up the learning for these robots. So first of all, I will yeah, present to you how a classic learning from demonstration procedure would take place. And what is often used for teaching robots simple things. So this is imitation learning, so a robot imitating a human. And one typical way of doing this is behavioral cloning. And that's almost similar to supervised learning, where we collect a data set of human demonstrations, where each demonstration consists of a trajectory. And each trajectory then again consists of observations and corresponding actions. So basically, given a certain state or observation, there's an action related to that, what the human did there. And then we try to train a model. Perhaps some of you are already very familiar with this, but I'll introduce it briefly anyways. And then we minimize some loss between the actions of the model that we're training and the actions from the humans we have in the demonstration data set, give them the observation in the demonstration data set. And this model can be, for example, a neural network or a Gaussian process, or any kind of model that maps observations to actions. And then after this learning phase, what's typical in behavior cloning, you just execute the model. So you acquire an observation, for example, an RGB image and a language command, and then this model outputs an action, and the robot executes this action. But to this classical behavioral cloning practice, there are some downsides to doing this way, especially doing this in this sequential way of first training offline and then executing the policy. So one of them is that errors might compound, and this results from the following phenomenon. So if these models are usually only valid close to the observations in the demonstration data set. So as soon as the robot sees something it hasn't observed in the demonstration data set, it might make a mistake. But the problem is that when it makes a mistake, then it's even more likely that it will observe something that was not in the demonstration data set, because we might be learning from human teachers that demonstrate perfect behavior, so you never encounter errors. And then the robot also doesn't know how to recover from these failures, and then you get these compounding errors. So that's one of the problems with standard behavioral cloning. So alternatively, like Jens already mentioned, we can also learn interactively through interactions with humans. So we have a human in this learning loop, and we don't have a strict separation between training and execution, but we are basically training also while executing. And this interactive imitation learning paradigm allows for very natural or intuitive teaching, for example, through language even, or through demonstrations or for feedback. And this allows us to obtain rich data sets. And with these rich data sets, I mean that we are executing the robot policy, so the robot might sometimes fail, and then we can collect demonstrations, for example, in a failure state and learn how to recover from these failures. And also this allows for very high level flexibility in the type of feedback. So we can learn from demonstration, but we can also learn from reinforcement. So basically a reward signal or preferences where the human is indicating what action it likes better. Absolute corrections, so where we actually move the robot and say this would be better, or relative, so you move more to the left or to the right. That's all possible in this interactive learning paradigm. And something I have focused on with my partner method is on the gating. So in this type of control, you have a robot sometimes acting and sometimes a human acting, and how do we gate control between the robot and the human? So that's what I focused on in this partner method. And basically in this interactive imitation and method for a pick and placement task, we query the human for demonstration whenever our model is uncertain. And there are basically two reasons for doing this. So first of all, uncertainty is related to failures, and in order to keep the number of failures at a minimum, if we're executing some task while also learning, we don't want to fail too often. So therefore, it would be good to hand over control whenever the robot fails. And on the other hand, this also prevents us from acquiring redundant demonstrations. So the demonstrations are costly in interactive imitation learning because it can be quite tedious for a human to provide a demonstration. And therefore, we would like to minimize the number of demonstrations and also have a rich data set while having a few demonstrations. So we don't want to have the same behavior demonstrated over and over again. So in practice, this works as follows. So we observe the environment, we obtain RGB image and language command, goes into our model, then we check the output of our model, and we check if the model provides a single distinct action, or whether it's kind of confused between different options of actions. If it's very confident, we execute this action, but whenever it's not confident, we hand over control to the human, and we query for a new demonstration, aggregate this demonstration to the data set, and update our model. So yeah, in one sentence, this is when there's action ambiguity, no single distinct maximum in our model, the robot should hand over control to the human and learn from new demonstrations. We formalize this in the same way as transporter networks by Annie Zhang and his co-authors, and that's yeah, kind of yeah, it's a behavioral cloning kind of way of formalizing this. We have a mapping from observations to actions, in this case a pick and a place action, and we have two value functions, one for picking and one for placing, and these are pixel-wise value functions. So for each pixel, our model outputs a probability of yeah, kind of how likely it is that it will be successful when picking there. And then we also collect demonstrations, and these demonstrations consist of trajectories that are tuples of observations and actions. And then the model we use is Clipboard, so that's basically an extension of transporter networks with language, and incorporates the CLIP model. This CLIP model is a foundation model developed by OpenAI, and was trained on many images and their captions that are available on the internet. So huge amounts of data. And in this way, we can kind of leverage this prior knowledge that's in this foundation model and extract features from the image and from the language command, and reduce the input to our model in order to speed up learning. And then our method works as follows. So we get a language command, in this case, pick the yellow book and place it in the red bowl. We get an observation in the form of an image. Then we get these pixelized value maps. And there's a maximum there that you usually would execute. But whenever there are multiple maxima that are close or have similar values, we query the human for new demonstration. We do this for picking and for placing. And in the end, you can learn this yeah, simple pick and place table manipulation task in this fashion. So we carried out some experiments to quantify whether this actually helps. So here we have some simulation results where we acquired 500,000 and 1,500 demonstrations, and we compared it to this non-interactive baseline. And we see that using this form of interactive learning, we can actually obtain similar performance with up to 20% fewer demonstrations. Yeah, this is probably due to the fact that we acquire fewer redundant demonstrations, and maybe also we learn some recovery behavior. So next to the simulation results, we also kind of yeah, did a demo with this method that's kind of similar to a diesel engine assembly task, but very much simplified. So we use a very simple model of this diesel engine. And we have simple bolts that we would like to place into this diesel engine, and based on speech commands by some human operator, and we would like to teach the robot to execute this task. So yeah, this is what this looks like. So we obtain an RGB image, adapted image, and a language command, and then we have this kind of simple diesel engine with some bolts, some tubes, and then we would like to use natural speech to execute this task. So there are a few challenges in this task. One of them is the unstructured speech that I mentioned. So ideally, we would like the human to be able to just speak naturally, not with a certain language format. So it could kind of, command the same task in different ways. And also we would like this method to be robust to variations in the setup. So when we change the lighting conditions or change the orientation of this diesel engine, it should still be able to work. And we would like to learn from as few demonstrations as possible. And then, so this is kind of the check that we do. We observe the environment, then partner decides whether the model is uncertain or not. And when it's uncertain, we ask the human for a demonstration. In this case, the human demonstrates where to pick and where to place by clicking with the mouse in this GUI. And then the robot, either executes the demonstration or it executes
Hey robot, please put the red thing in the middle.
And then, in the end, we can also do this. We learn to solve this task sequentially, and we can provide natural speech. So, for example, here, robot, please put the red thing in the middle tube, and then it learns to execute this task. And it might sometimes still vary for a new demonstration whenever it's uncertain. So so for the future, we're still not there to realize the dream that Jens was talking about. So there's still many work to be done, and these are very simple examples of simple tasks. So some things we would like to work on is, for example, to improve the uncertainty quantification. So perhaps we could do this in a more optimal way to better filter out when we should add from the demonstration, when this will be relevant, in which states we would like to have a human to demonstrate or provide feedback. Also, we would like to reduce the cost of demonstration collection, since this is usually the main bottleneck of these methods. One thing we're looking in is, for example, also learning from the robot's failures. Can we learn something from that? Also, we would like, of course, to extend this to more complex problems, go beyond these simple pick and placement table manipulation tasks. And another thing, we're also working on is to allow for an intuitive trade-off between robot failures and the number of queries. So on the one hand, these failures might actually be valuable because you can also learn from these failures and then learn how to recover from them. On the other hand, you don't want to fail too often, and also you don't want to bother the human too often and ask for demonstrations all the time. It would be nice to have that possibility to trade this off intuitively and not having to tune by the parameters, for example. So that was it from my side. And maybe we can do the questions now if they're there.
Yes, we can take some questions maybe in between. Do we have some questions in the session? I have some myself, which I can ask for some, just mostly clarifications than questions. If you can go back to slide 12. I think it was 12. Yes, yes, that one. So here, the train procedure is purely imitation in this work, right?
Yeah, that's correct.
Okay, so you assume that the database contains only optimal decision, I would say. So something that is the robot you want to perform, like it's
In this work we have the assumption that these demonstrations are perfect. So in practice, that's of course not always the time. So what we did in simulation is that we added some some noise to these demonstrations.
Mhm.
But of course, in practice, you might also have imperfect demonstrations, and also people working on how to deal with that. So, for example, filter out these imperfect demonstrations or learn how to deal with that. But in this specific work, we have the assumption of close to perfect demonstrations.
Okay, the demonstrations only come from the human, right? In these examples, it's
Yeah.
not okay. And can you clarify as well a little bit how is the loss computed for the Q network you use here?
So if you remember, we have this pixelwise value function. So that's kind of the output of this network, and we obtain a demonstration for from humans. And so we have an observation in our demonstration data set, which are these this image, this depth image, and a language command. And then we put this into our model, and our model will output a pixel-wise a value map. And this is kind of a distribution over all pixels. So this value map will sum up to 1. And then we have a demonstration for a human, where we have a human picking an object at a certain pixel location and placing it at a certain pixel location. So what we do is we have the human output is then basically 1 at this pixel location, where and 1 where it's placed, and then we have our distribution output by our model, and then we calculate a loss between these 2 distributions. And in our case, we use the cross entropy loss. But it's kind of similar to how you would calculate a loss in like a classification problem, where you have a distribution over possible classes, and
so
then calculate the cross entropy loss over the prediction and the expert output.
Okay, so basically it's the same as if each pixel were a class and you were using classification.
Yeah, exactly. That will be the same situation.
Okay, I understand. And the pixel itself, is it I mean maybe the shape you want to grab is not one particular pixel, that's the one you click in the demonstration. It's more like an area or something like that, isn't it?
Yeah, true. So it's kind of strange that we assume that the ground truth is this spike where there's of 1 at 1 pixel location and 0 at other locations. But this problem is kind of solved by the type of loss that is used, so by this cross entropy loss, because this loss will go to infinity whenever your model outputs whenever they don't share the same support, so to say. So if our model would output something that is 0 at the location where the human picked, then our loss goes to infinity. So this results in the model kind of assigning some value everywhere, and close to where it thinks that is the perfect location, it will create this kind of hill shape. But it's indeed not perfect, especially not if you have various options where you could actually pick.
Yeah, I see. I heard of at least one network doing image plus label into segmentation. I think Meta did segment anything. It was some the work, but I don't know the actual architecture of the network and how it is trained. But I know they output from an image and text, they can output segmentation so that you can easily select an object or something. But I have no idea how it works exactly under the hood.
I think that's close to your work, right, Runyu?
Mm.
So yeah, my colleague Runyu did something with PLMs in order to extract objects from images in such a way.
And maybe one
We'll
last
talk about it later.
one last question, and it's you said it's costly in terms of database, and sorry if I missed that, but how big is your training data sets in the example you gave? For example, with your setup, how many examples do you need for the setup to work properly according to you currently?
So in this simulation task, we use a simplified model, and that's less data efficient. But yeah, we're basically using this in this case this clipboard model, and clipboard model yeah, is kind of able to do reasonable simple tasks after 100 demonstrations, something like that. So
okay.
For the engine, how many demonstrations?
I think something in that range, so 100 or maybe a bit more. I don't know the exact number.
Okay, I see. Thank you.
And thanks, Jelle, for this introduction. And my name is Runyu, and Jelle and Zlatan and Jens are my supervisors, and we are focused on using some large language model to guide exploration of the reinforcement learning. First, I will talk about the introduction and motivations. To solve language condition robot policy learning, there's commonly two ways. The first one is to train a end-to-end learning policy. For example, Jelle have introduced his work and also clipboards that all use end-to-end learning method. And they have large observation space, large action space, and large network. And if you want to solve it by reinforcement learning, it is hard to train because it takes so many time to converge. And the second method is to use foundation models for high-level planning and use pre-trained low-level robot policy to execute it. And one representative works is Zlatan in 2022, and they use large language models to do high-level planning based on the affordance grounding, and they execute those actions by clipboard or other low-level robot policy. However, those large language model might make mistakes in high-level planning, and pre-trained low-level policy might be wrong with unseen scenarios. So what I plan to do is to combine the foundation models with reinforcement learning. And because foundation models have the reasoning capacity, and it has some prior knowledge to guide reinforcement learning to do some exploration. And reinforcement learning also have some real-world grounding because it's interact with the environment and have the reward signal. So it can alleviate the problems that foundation models might make some mistakes. And so my work is sounds like combination of those two options I mentioned before. And our main contribution is to use foundation models to guide explorations for reinforcement learning, and also use foundation models to extract observation space. And we formulate our problem as a Markov decision process, which is commonly used in reinforcement learning community. And first, you have an environment, and your robot agent gets a state. And for example, our task setting have a state as the user command input and also the observation image along with the robot state. And the policy would, based on your state as input, get an action that maximize the aggregate reward. And in our cases, the action is a prime index that indicating whether you should pick workplace and pixel positions in 2D. And after the agent takes the actions, the exploration will give a reward feedback on this step. And it will also have the state T+1 of the next step. And it will do the iteratively in this loop, and reinforcement learning will learn from those reward feedback to get the optimum policy to. And I will talk about our method and framework. Firstly, our method, including using foundation models to extract affordances and languages. And we use vision language models to segment image input informations into some image props, and using large language model to extract the goal space. And after those observations goes into the reinforcement learning policy, our large language model would generate codes program to guide reinforcement learning to do explorations. And also the action space is a residual action space. For example, it is a relative action corresponding to the image center. For example, if it is a block, it will goes to the center to pick it. And if it's some irregular shaped letters, it will find the distribution around the center of the image crop to get a good pick or good place. To be detailed, we use vision language model to extract affordances. And vision language model are the models that train on large-scale vision image data, vision language data, and which can work well in some situations that you do not see before. For example, we use VILD as our open language detection to detect the image drops in the in our given image. And also some people use segment anything to find some segmentations given what task you are doing. And it's a widely used pipeline in robot perception. And for our problem, given the object category input and also the image input, the vision language model will draw the bounding box inside your image as the picture shows. And we also, based on the image center, it's a center of the bounding box to draw a image crop with fixed resolution. And our main contribution is our exploration. And firstly, we directly use action generated by large language model instead of reward shaping. For example, other works that use reward shaping to guide reinforcement learning, but we just use action generated by large language model. And we want to collect some data in reinforcement learning that close to both current policy distribution and halo state distributions, and put those data inside the off-policy reinforcement learning. And the quality of the replay buffer in off-policy reinforcement learning is deterministic to the result. And our exploration policy is inspired by epsilon gradient that we will, at each time step, we will draw a random number from 0 to 1. And if it is smaller than threshold, we will do something that large language model generated. And otherwise, we will do something based on the reinforcement learning current policy. And we would like to use CODES policy as our large language model exploration. CODES policy is a literature that from 2022, and they use large language model to generate Python codes and execute those Python code for doing some zero-shot action. And they demonstrate that large language model can write robot-centric formulation of language model generated programs. And we also use it as our exploration CODES policy, which is at every time, which is before the training, we will let the large language model to generate code, Python code. And when we are training, when we need to do some large language model based exploration, we would execute those Python codes and do something. And for our policy network, we first use put those image crops into object encoder, and then concatenate it with its own object positions, robot states, and language command into a sequence of vector, and then it goes to self-attention layers and some MLPs, which are policy and critics network of the reinforcement learning. And then it will have an action. And those whole network is trained based on the reward from the environment. And I will introduce the detailed implementation of our work. And first is the exploration code as policy. And why we would like to use code? Because if we prompt large language model every time that we want to do some exploration, for example, reinforcement learning would do millions of steps to train a policy. So if we prompt large language model every time, it would be extremely expensive and time consuming. So if we use code, we can prompt code once before the training phase and then do execute those code every time. So it's less expensive and less time consuming. And we would like to use hierarchical code as policy. The code as our exploration code consists of a high-level action code and low-level action code policy. And it is generated by GPT-4 Vision, which is a GPT version that can handle vision image input modalities. And it will generate OpenCV or NumPy programs for our low-level action policy, which of course could be infeasible or suboptimal because GPT-4 is not that clever. For example, in this picture, we're picking the letter V, O, and R, and two of the candidates cannot work at all. And three results do not make that sense. They will catch the edge. I can't see. Move the mouse over. Yeah. Oh, sorry. I need to move my mouse here. So those are the candidates code as policy generated by our large language model, and some of them, two of them, the candidates 2 and candidate 6, they cannot do something meaningful at all, and 3 of them are not optimum. For example, the first one, the third one, they want to pick at the age of letter, which is proved to be unstable, and this one seems to get a whole box of the letters, but it's not that efficient. And this one, it is badly got. So we let the large language model to generate candidates, and we choose the best one. Even though it's the best one, it also has some suboptimum. For example, it wants the robot to pick in the center. However, it's not working. So, but it is not a big issue for us because we just use it as exploration. And for reinforcement learning, we can learn from those mistakes and work beyond that. This is our high-level prompt, and it consists of introduction of task setting and also a list of robot API, which means the functions that you can use in the result, and along with templates, and also with some examples and current foundation models work that shows the examples are very useful when you write some prompt and want to find some results that you want. And we will put the prompt into GPT-4 and it will give us code that we can execute. And this is a view that we prompt in OpenAI Playground. And we give them the prompt examples and consists of templates and also the examples and there are a long list of examples. And it will write something on its own. And this is some demonstrations of how large language model generates the codes. And for the prompt for low-level actions, which is quite different from the high level, because high level, you want to decide which object you want to pick or place. And for low level, you will find some affordance maps or find something that really close, really relevant to your task setting. So we provide the large language model two images, and the first one demonstrating the task settings, and the second one describing how the image crops looks like. And the prompt is very similar to what I introduced for the high-level prompt, and it will generate several candidates, and we, after evaluation, we find the best one. And I will introduce some experiments and results. And to evaluate our work, we just have two tasks. The first one is the short horizon task, which is put the letter in the bowl. And the second one is a long horizon task, which is put all letters in the bowl with the same color. And the experiment, our first experiment is to validate our method can speed up the convergence of reinforcement learning. And we also want to analyze the influence of the large language model exploration frequency, which is the ratio that the large language model guided exploration step over all steps that reinforcement learning do. And the dashed line in this figure is the average episode reward of the exploration policy only. And it will act as a baseline of our work. And also, I plot a 0% blue line, which is our method without large language model-based exploration. And as you can see, it can sometimes converge, but sometimes it will also fail because the variance, the blue region, is huge. And when the exploration rate goes from 10% to 50%, there's no obvious difference between them, and they can all converge and work beyond our baseline. And after the exploration rate is larger than 50%, it is more like offline reinforcement learning. And the current policy do not get much updated, as you can see in the figure, in this figure. The brown line and the brown line and the pink line. And this is the figure of the long horizon task. And it shows similar trend to the short horizon. And when it's 0% exploration rate, it do not converge at all. And as the exploration rate goes from 10% to 50%, the converge is going faster. And when it goes after 50% of the exploration rate, it's just do not converge. And our second experiment is to show that our method can avoid low-level error, especially in unsafe scenarios. And we have three baselines. The first one is the codex policy, which is our exploration policy only. And the second one is Socratic model, which is a work in 2022 that combine different kinds of foundation models. It uses large language model to do some planning and use vision language model as perception. And it can also use clipboard as the low-level policy. Another our baseline to compare is in a monologue. It is also a work from 2022, and you also use large language model for planning and use grounded closed-loop feedback as a large language model grounding. It also uses clipboard as a low-level global policy as Socratic models. And this is our result. And we also introduced some special situations that allowed overlapping when initialization, which means in initializations, you have a letter that have some overlap with the both, and which is not common in our previous training situation. And from this result, we can see that the clipboard-based method do not set robust to the unseen scenario compared to our method. And our method have a low-level error rate. And this video is we do zero-shot transfer from the simulation to reality. because when we extract observation space by using vision language models to segment the whole image input into some image props so that they can avoid some distractions, for example, the light or some other noise. So it can zero shot transfer to reality to some extent. And for conclusion that we demonstrate that our work, our method can accelerate reinforcement learning training. And we can surpass other foundation models work in success rate. And we can also transfer to from simulation to real world in zero shot. And for the future, we want to do some more generalized manipulation tasks and enable large language model to correct itself during the training. For example, our current method just prompt large language model once before the training. However, it is not that robust and it might be failed, or sometimes we require too much prompt engineering. So we want to use reinforcement learning to have some feedback on the high level and use those feedback to correct the large language model. And thank you for your listening.
Thank you very much. Do we have time for some questions on your side?
Sure.
Okay. So we can take some questions.
For each of the papers, there's also a homepage with code and video and stuff if you want to check it out.
Okay, thank you. That's nice. And I can ask a few questions maybe.
Sure.
If there are none. Again, there are as well some clarification questions. When you don't explore using LLM, what is the underlying exploration policy? Is it? I mean, I believe it depends on the underlying RL algorithm that you use. So which underlying RL algorithm is it, and what exploration is done when you are at 0% LLM explore in this example?
So for the large language model, I use GPT-4, and it will generate some codes, and those codes are our exploration method. And when we do not do the exploration, we will do some reinforcement learning exploration on its own. For example, for if it's something that's based on our reinforcement learning current policy. And if I understand correctly about your question.
Okay, but what is the underlying RL algorithm itself that you use here?
For the reinforcement learning algorithm, I use soft actor critics.
Okay, so it's off policy algorithm.
Yeah, it's an off policy.
Because in a soft actor critique, you can also use so the exploration strategy is based on sampling from the distributional output of SAC as well, right?
Yeah.
If it's not, if you in the case where you don't use LLM, I mean, SAC is not set as deterministic in that case, right?
Yeah, it's not fully deterministic. During training, this assay is still a stochastic, and
Okay.
it is on exploration.
Okay, I see. So just to be sure as well, so in your code as policy approaches, what happens, because you get a lot of code, I guess, that is not usable in practice, right? Because of syntax error or infinite loops, as you said. How do you handle this in practice?
I will go to the slides.
I think you mentioned it at some point.
Because some of them are not optimal and some of them are not working. So at the beginning, I would let the large language model to generate so many candidates, and I would choose someone that with the highest performance, and just leave the rest of those candidates.
Okay, but it's hard to evaluate the code itself, isn't it? I mean,
I think it's not so hard to evaluate because it's just to generate a fullness map, and it is quite obvious if the some of the map is meaningful or some of the map is not meaningful.
okay, but I mean, you can evaluate the output of the code, but for that, you need for the code itself to work, to execute. So I think you have a lot of engineering, right, to sandbox and limit the execution of the code produced with such a setup, isn't it?
Yeah.
Yes. Okay. Okay. I don't have many more questions. If we don't have some other question, maybe we can stop the session. I think it's time anyway.